We are surrounded by computers, right? They're in our pockets, on our desks, everywhere. But have you ever stopped to think, how do we actually talk to them? How do we take an idea that's in our head and get it into a machine that, only gets ones and zeros?
Right, so that's the big question. How do you tell a machine what to do? I mean, you can't just talk to it like you would a person. At their very core, computers run on a kind of logic that is completely, totally alien to how our human brains work. And that right there is the fundamental problem. You've got this huge, massive gap between our messy, creative, sometimes weird human thoughts and the cold, hard, precise logic of a machine. So, how would we bridge that gap?
Well, that's exactly what we're going to get into today. The answer, the solution to this whole puzzle, is something called a programming language. You can think of it as the ultimate translator. It's literally the bridge, this special man-made language designed specifically to turn our ideas into a set of instructions a computer can actually understand and execute.
Okay, so you might be thinking, what's the big deal? Why can't we just use English or any other human language? Let's dig into why that doesn't quite work and what the real challenge is when you're trying to talk to a machine.
It's a really interesting paradox when you think about it. Computers are these unbelievably powerful tools, right? But at the same time, they're incredibly dumb in a way. They're super literal. They have zero concept of what you meant to say. They can't guess your intent. So if you miss one tiny comma or you forget a single step in a recipe, the whole thing just falls apart. They only understand exactly what you told them, nothing more, nothing less. And this need for absolute, perfect precision, it made the early days of programming an absolute nightmare. Let's take a little trip back in time and see what the pioneers of computing were really up against.
Whoa, okay, look at this. This shows the problem perfectly. On the right, you've got a super simple human thought. Add 5 and 3. Easy, right? Now look at the left. That is what the very first computers actually understood. A raw, mind-numbing stream of ones and zeros called machine language. Can you even imagine trying to write thousands of lines of that? It was slow, it was a nightmare to find mistakes, it was just brutal. Yeah, this was just not going to work long term. It was totally unsustainable. As people started dreaming up bigger and better things to do with computers, it became painfully obvious that they needed a better way, a more human-friendly way to get their ideas into the machine. And that desperate need, it sparked a full-blown revolution, a complete and total rethinking of how we talk to computers. This led to the birth of what we now call high-level languages.
And here it is, the key moment, 1957. That's the year a language called Fortran was born. Fortran is widely considered to be the very first true high-level language, and believe me, it changed absolutely everything.
I love this analogy because it's just so perfect. Think about it. Before Fortran, programming was like being a mechanic who had to build a car from scratch, piece by painful piece, every single time you wanted to go somewhere. High-level languages, they handed programmers the keys, the steering wheel, the gas pedal. Suddenly, you could just drive. You could focus on where you wanted to go instead of worrying about how every single part of the engine worked. So how did this magic trick work? It was all thanks to a seriously clever piece of software called a compiler. The process suddenly got a whole lot simpler. Step 1, you write your code in a language that looks a lot more like English. Step 2, the compiler swoops in and acts like a master translator, turning all of your human-readable code into the ones and zeros the machine needs. And finally, Step 3, you run the translated code. Boom, done. Now, of course, for these new languages to work, they had to have rules, right? Just like any language. The first, and maybe most obvious set of rules is called syntax. The easiest way to think about syntax is just grammar. It's a set of rules that tells you how to put your code sentences together so that they're formed correctly. Take this classic sentence, colorless green ideas sleep furiously. Now, from a grammar perspective, this sentence is perfect, flawless even. You've got your adjective, your noun, your verb, your adverb. All the pieces are in exactly the right spot. The syntax is 100% correct. But it's complete gibberish, right? It means absolutely nothing. And this brings us to the other crucial half of the puzzle. Semantics. Semantics is all about the meaning. In programming, this is huge. You could write a line of code that is syntactically perfect. The grammar is all correct. But if it tells the computer to, say, add the number 5 to the word banana, that's semantically nonsense. The computer won't know what to do, and your program is going to break. So once we cracked that basic problem of translation with compilers, something really incredible happened. The floodgates opened.
Instead of just having one or two languages, we saw this massive explosion of new ones, with each new language being custom-built to solve a specific kind of problem. You can really see it on this timeline. New challenges always lead to new languages. Back in the 50s, the big challenge was scientific computing, so we got Fortran for math. Then, in the 70s, we needed to build operating systems from the ground up, so C was invented. Fast forward to the 90s, the internet is booming, and suddenly we need languages like Java, Python, and JavaScript to build the web. And now, in the 2010s and beyond, the focus is on performance and safety, so we get languages like Rust, Go, and Swift. So why so many? The big reason is that different languages are built around different ways of thinking about a problem. For example, an imperative language like C or Java is basically like giving the computer a recipe, a strict step-by-step list of commands. But then you have a functional language like Lisp, which is more about describing a set of mathematical functions. It's not that one is better than the other, they're just different tools for different jobs, designed for different kinds of brains.
Okay, so where does all this leave us today? Are we just going to keep inventing more and more languages where we type out text? Well, maybe not. The very idea of what a programming language is still evolving.
Because here's the thing, programming isn't always about text anymore.
Just take a look at this. Yeah, for sure, traditional text-based languages like Python are still king. But there's this whole other world of visual languages that's growing like crazy. We're talking about tools like Scratch or Blockly, where you can build real, working programs just by snapping together colorful blocks, kind of like digital Legos. It's making coding accessible to way more people, including kids, which is awesome.
And that's the key takeaway here. Programming languages aren't these ancient, dusty rulebooks. They are living, breathing things. They are tools that we, as humans, invent, and we constantly change and adapt them to solve the new challenges that we face.
Which brings us to a really mind-bending question for the future. As AI gets better and better at writing its own code, what does the next programming language even look like? And maybe the even bigger question is, will it even be designed for humans to use? Or will we be building languages for the machines to talk amongst themselves?